We've already talked about methods for organizing qualitative data, and now we're going to talk about methods for organizing our quantitative data. Some new terms for you will be observations being grouped into something that we call a class. A class is also known as a category, or you might see it be called a bin, and that's very common in Excel. So they will often call the classes a category or a bin. All right. So once we group our quantitative data into a class, we can then construct either a frequency or relative frequency distribution in the exact same way that we did for our qualitative data. And so one of the reasons for grouping is to organize the data into a sensible number of groupings or classes in order to make the data more understandable or accessible to people. And so there are some common sort of guidelines for grouping quantitative data. For example, we want the number of categories that we have to be small enough that we can actually summarize the information, but it also has to be large enough to actually show the characteristics of the data. Each observation must belong to one and only one class. And so we'll talk about these three different types of grouping so that we know exactly how we can make that happen. And whenever feasible, all classes should have the same width. And again, we'll talk about some of these methods as we go through the three main methods, including our single value grouping, our limit grouping, and our cut point grouping. So we're going to start out with our single value grouping, and I'm going to use an example of bunnies. And so shown here is my bunny. She's passed away now, but her name was Coco, and she used to frequent my videos all the time. All right, our first type of grouping is called single value grouping, and this is really analogous to the qualitative data grouping. It's used mostly for discrete data where we only have a small amount of values or number of values. So in single value grouping, we use classes in which each class represents just a single possible value. And so you can see here, this is the survey done of students. I think there was 100 of them on the number of bunnies that they own. And the staggering amount of people that owned no bunnies is crazy to me because they are the best pets. But what you can see here is that most people owned 0 bunnies, and then it went all the way up to 5 bunnies. And we could create a relative frequency based on this categorization on the number of bunnies. So the single value grouping is pretty easy to employ, but we don't use it a whole lot with a lot of our quantitative data. And so there are some other methods that we're going to discuss. And the next one is limit grouping. And in this method, each class consists of a range of values. So the smallest value that could go in a class is called the lower limit of that class, and the largest value that can go in that class is called the upper limit of that class. And so this method of grouping quantitative data is called limit grouping because you're putting limits on what can go in there. Now, this is very useful to us when we have data that is expressed as a whole number, and there are just too many of those distinct values to actually use the single value grouping. It would just make it out of the charts to be able to look at it and understand what it is. There are a couple of definitions we should go through before we continue the discussion on limit grouping. So as I mentioned before, we have the lower class limit and the upper class limit. Now the lower limit is the smallest value in the class, and the upper limit is the largest value in the class. And so you might think to yourself, well, how am I to know where to start? Where do I go to find my lower limit? And usually that will come from a class width. And so in a question, you'll be asked to do some limit grouping and use a class width of, for example, say 10. So the class width, you can think of it as how wide each group or bin is going to be. And you can find it by subtracting the starting number of one class from the starting number of the next class. And more officially, it is the difference between the lower limit of a class and the lower limit of the next higher class. So in this example here, class 1 is 50 to 59 and class 2 is 60 to 69. So if we wanted to calculate our class width, then we would take 60, subtract 50, and that would equal 10. And that means each class covers 10 numbers. And so you're often told we want a class width of 5 or 10 or whatever it is. Now, we also have something called the class mark. Think of the class mark as the middle number of your class, and you can find it by averaging the lowest and highest numbers in the class. So, for example, class 1 is 50 to 59. And so you add them together and divide it by 2, and you would get a class mark of 54.5. And that's the representative value for that class. So a one-sentence memory trick: class width is how wide the group is, and class mark is the middle of the group. And of course, the best way to learn is to actually just do an example of it. So I definitely recommend that you pause the video and do these examples with me, because it's always easier to watch somebody else do it. And then when you go to do it yourself, you might go, uh-oh, I don't really know what I'm doing here. So in this example, we're going to be talking about the maturity of investments. The table shows the number of days to maturity for 40 short-term investments. And it's asking us to use limit grouping with groupings by tens to organize these data into frequency and relative frequency distributions. So it is telling us that it would like for us to have a class width of 10, which is really going to be helpful for us when we start to think about where we should start our classes and then end them. My recommendation to you guys is always to list your numbers in ascending order. So going from your lowest number to your highest number. And so I've done that here. I've taken all of that information and I've listed it. Now, what you'll see is that the lowest number that we actually have is 36, and the highest number that we have is 99. So when you start to think about your class width of being 10, you're going to not start at 36. That doesn't make a ton of sense, but it would make sense for our first class to start at 30 and then go to 39. And so I've shown below in this sort of orangey colored chart that it's a class width of 10. So 30 is number 1, 31 is 2, and so on. And 39 is going to be our 10th digit. So we're grouping by tens. The lowest is 36, so we'll start at 30. That's a decision that I am making, and those are decisions that you are going to have to make as well. No one's really going to tell you what to do, but they will say, hey, I want the class width to be, this big here. So you'll make it, you'll put it together and you'll make it logical to work for you. So again, I listed in ascending order, so it's going from smallest to highest so that I can establish where I would like things to start and then where I would like everything to end. Next, what we'll do is we'll start to make a frequency and relative frequency distribution. So from 30 to 39, you can see that there were only 3 different individual data points. So we'll put the tally of 3, add the frequency of 3, and then 3 divided by 40 is equal to 0.075. So from 40 to 49, you can see that there was only 1 entry there. Only 47 falls in there, so it is given a 1. And you go down in this format so that every number only fits into one category. So 30 to 39, and then there's no overlap between the 40 to 49. So just take a step back for a second, because what if this data had decimal points in it? Well, that becomes a problem. You can't use limit grouping when you have decimals. It's particularly useful when the data are whole numbers, and then we can't use that single value grouping, which leads me to the next type that we're going to practice, and that will be our cut point grouping. The third way of grouping quantitative data is to use our class cut points. And this is so continuous data, so data with decimal places, can now be grouped. So the same as with limit grouping, each class is going to consist of a range of values. The smallest value that could go in a class is called the lower cut point of the class, and the smallest value that could go in the next higher class is called the upper cut point of the class. So the lower cut point of a class is the same as its lower limit, and the upper cut point of a class is the same as the lower limit for the next higher class. I know it seems confusing, but once you start to do an example of it, it will make a lot more sense. So the method of grouping quantitative data by using these cut points is called cut point grouping. And we use it when our data are continuous, when we have decimals in there, and we need to make it so that we can contain each individual number into just one single category. Okay, this example here is showing the weight of 18 to 24-year-old males in pounds. And it is asking you to use cut point grouping to organize these data into frequency and relative frequency distributions. It is saying to use a class width of 20. So we know that the size of each bin should be 20, but it's also telling us what our first cut point will be, and that will be 120. So sometimes it will give you this information, other times it won't, and you're just going to have to use logic to make that decision. And that's more in a workplace scenario. So once again, I've taken all of the data here, and you can see that I have arranged it in ascending order. So I start from the lowest and go all the way to the highest number. So because we are going to use that first cut point of 120, and we know we have a class width of 20, our first class is going to start at 120, and then it's going to go to 140. But what I should mention here is that the column for weight is not actually showing or saying exactly what it should. That first column category, what 120 to 140 actually means, is 120 to under 140. So for example, 139.99999 could still fit into it, whereas 140 wouldn't be in that category. So you'll often see it shown in the book or in examples as 120 to under 140 or whatever the number is. They'll be under the other one, or they'll use less than or greater than symbols. And that's just so that we know that there are decimals as well in here. So again, we've got the class for is for weights of 120 and up. So that's not including weights of 140. The largest weight is 278.8. So the last class in the table that we're going to have is 260 to under 280. And all we have to do again is group the data and then go ahead and count the frequency. So if we go back to the original, if we went through 120 to 139.9, we would find three numbers divided by our grand total of 36, and that gives us a relative frequency of 0.083. So what you'll see here is that everything fits into only one category, but it's considering all of the decimal places in this. Now, one thing that I want to note is that relative frequencies will always sum up to 1. There are times when there'll be rounding error, and so it might sum up to 0.999, for example, and that's okay. That discrepancy occurs because the relative frequency got rounded so many times. So this is called rounding error or round off error. So if it's somewhere within the realm of 1, you're usually fine. If it's far off from 1, then you've probably done something wrong. And again, the best thing that you can do in these situations is to just practice. So in this example here, I have the greater than, less than symbols so that you can get an idea of what I mean by saying, 120 to under 140, for example. So it's 0 to greater than or less than just 1, for example. So in this practice here, it is the oxygen distribution in marine sediments, and it's asking you to use cut point grouping with the first class being 0 to just under 1. So let's pause it. Let's do this together. If you're going to pause this video, start by taking all of that data and putting it in ascending order. That will always help you to figure out what you need to do next. All right, so you can see here that we've got 0 to just under 1, and there was only one data point that fell into that, and that was 0.7. And then 1 to just under 2, there were 10 data points that fell within that, and so on from there. Now, what about 4 to just under 5 and 5 to just under 6? There's nothing there. So should we remove that information? And the answer to that is absolutely not. No information is also a type of information. And so this is how you will do your cut point grouping. Now we're going to do some of this on Excel in lab, so you'll get more practice with it. But I would recommend that you do practice it by using the practice worksheet that I will post on Blackboard. They're not for marks, but I give you the answer key. And also, if you have the textbook or you want to use the OpenStax books, there will be some extra practice in those as well. Okay, so we looked at those three methods for grouping quantitative data, which are single value grouping, limit grouping, and cut point grouping. And so you might ask yourself, well, how do I know which one to use and when to use it? It's actually quite easy. With the single value grouping, this is discrete data, like the count of bunnies, and there's only going to be a small number of distinct values. If there's more, then you would use limit grouping. And so use when the data are expressed as whole numbers and there are too many distinct values to employ just the single value grouping. Easy peasy, right? Discrete data. Now with the cut point grouping, this is when your data is continuous or they're expressed in decimals. If you see decimals or it's a continuous data, well, you're just going to use cut point grouping. And the basic way that you kind of go about doing it is pretty much the same for it. You just have to make sure that you are grouping quantitative data into your classes. And how do you choose those classes? Again, it can be very subjective. Most of the time, we're going to be doing this by technology, and at the same time, you'll also be asked or given more information in the context of a question so that you know if you're grouping by 10, 20. If it doesn't say, then you get to choose. Okay, gang, we're going to move into looking at visuals for quantitative grouping. A lot of these visuals, just kind of looking at it now, pretty much all of them you will only do on a computer. The one that you will have to know how to do by hand is the stem and leaf plot. Dot plots are pretty easy to do by hand as well. The main types of visuals that we're going to talk about will be histograms, dot plots, stem and leaf plots, and we'll talk a little bit about density plots as well. And I promise I won't go on a rant about all of the ones that I dislike. All right, so let's begin with the histogram. A histogram is something that is used quite a bit, and it displays the classes of quantitative data along a horizontal axis and the frequencies or relative frequencies or percentages of those classes along the vertical axis over here on the side. So the frequency or whatever relative frequency, whatever you decide, is going to be equal to the frequency of that class. And so the bars are always positioned so that they touch each other. So for single value grouping, we use the distinct values of the observations to label the bars. So each value will be centered right underneath the bar here. But for limit grouping or cut point grouping, we're going to use lower class limits or the lower class cut points to label the bars instead. And of course, this might change depending on what you're working on and who you're working on it with. So the histogram is kind of analogous to the bar chart, but a histogram here is going to display the frequency or relative frequency of the quantitative data only. And so a histogram provides a graph of the values of the observations and how often they occur. In this example here, I'm just showing some data from single value grouping. And what you can see is that in A, the kind of blue chart here, this is a frequency distribution. And in B, this is a relative frequency distribution. And the reason why I'm showing you both of these is because the frequency histogram and the relative frequency histogram have proportionally the same shape. And the same would be true for if it was a percentage as well. And this result is because frequencies, relative frequencies, and percents are all proportional. And so in this example here, you can see that since the histograms are based on single value grouping, those distinct values are labeled right underneath the bars, centered at the bottom here. So this is the single value grouping histogram. And what you can, hopefully take away from this is that if you had different bin widths, this might tell different stories. So you want to choose the width that best shows the important features. Presentations can feature two histograms with the same data, but showing wildly different ways because there could be gaps in that or not. So a gap in a histogram means that there were no occurrences in that range, and that is information that we need. And in this histogram here, we're using limit grouping. And so the lower class limits, or if it was for cut point grouping, it would be the lower class cut point, are what we use to label the bars down here. And again, what we're showing here is the frequency and relative frequency and how proportionally they are very similar. They correspond to each other. And this one is not showing a percentage. And here's the final one with the cut point grouping. Again, it's labeling it, showing the 120 to the 140 range rather than just having that distinct label right underneath. One thing I wanted to point out was this symbol right here, these kind of double slashes. We use this on the horizontal axis to indicate that the 0 point on that axis is not in the usual position at the intersection of the horizontal and vertical axis. Now, we can make these modifications, but we have to indicate the fact that they have been made. And the reason why it was okay to make it on this is because obviously there are going to be no males, or generally no males between 18 and 24 that have no weight to them. They probably would be dead. Another type of graphical display for quantitative data is the dot plot. Now, a dot plot is a graph in which each observation is plotted just as a dot at the appropriate place above the horizontal axis here. Observations having equal values are just stacked on top of each other vertically like this. And they're very good for showing the relative position of data, but this is something that was done or more so used when printers were new and didn't have all of the options and ability to do what they do now. So to construct a dot plot, all you're going to do is draw a horizontal axis that displays the possible values of that quantitative data, then record each of your observations with a dot over the appropriate value and label that horizontal axis with the name of the variable. And so in this visual here, what it's showing are races with the winning times, the number of races. And so these are really good for small data sets, and they're more appealing than the stem and leaf plots, which I'll show you next. I am not going to lie to you guys. I find that my students really dislike stem and leaf plots and they have a hard time understanding them. I kind of get it because this isn't something that we do much with our hands anymore. We use a lot more computer functionality, but it's still important to go back and look at all of the different ways that statisticians have invented to display data. And one of those was by John Tukey, and he did a lot for stats, and we'll talk about it. He was from Princeton, and he created what we call a stem and leaf diagram, or a stem plot is another name that you might see it. So in a stem and leaf diagram, each observation is essentially sort of broken into two parts. We've got the stem, and then we've got the leaf. Now, the stem may use as many digits as it needs, but each leaf must just contain only one digit. So I've written out sort of the how to do this. So how to construct it first, what you're going to do is you'll get a list of numbers, and you're going to separate each number into a stem. So the digit that begins the number, so put that off to the left, and then the leaves. And these are the digits after the first number, and we're going to throw that off to the right. So you list the stems in ascending order, so smallest to largest, in a vertical column. And then on the left side, or you do that on the left side, sorry, of a vertical line. And then on the right side of it, you write each leaf that corresponds to the stems. So I'll show you guys an example because that's a lot of words that don't make a ton of sense when you're thinking about how do I actually go about doing this. All right, so you can see here that we've got cholesterol levels for 20 high level patients. And because these observations are 3-digit numbers, we're going to use the first 2 digits of each number as the stem. So for example, if you look up into this chart here, we've got 210, 217, 208. And what we're going to do is our stem in this situation is going to be 21, and then there will be a 0. Stem 21, and then we'll put 7 off to the side, 20, and we'll put 8 off to the side. So hopefully that's starting to make a little bit more sense. So once again, take all of this data and arrange it from the smallest number to the largest number. And what you'll find is that the smallest number is 199. So what we want to do is we want to take apart our stem and we want to take apart our leaves. So the stem here is 19. And then we would add a 9 because there is 199. Okay. So then let's look at 20. Okay. There's a lot of different numbers here. We've got the stem and it's 20, but there was a 20. So there must be a number in here that's 200. And then we've got a 20, so 202. So let's look in the chart here and see if we can find 202. And then it's 23. So there's a 203 in the chart. And we go on like that. So this one here on the left, A, this one here is actually showing when we've got just one stem. So there's only 119. But there are times where you'll be asked to do 2 lines per stem. So there'll be 2 19s, and there'll be a couple 20s and a couple 21s. And the reason why they do this is to split it up. So for example, if there's so many that are 20 something, they'll split it up into 2 rows. So you've got 200, 202, 203, and then 207, 208, and so on from there. So although stem and leaf diagrams have a lot of advantages over some of the classical techniques for grouping, they also do have some drawbacks. One of the drawbacks is that I find students find them confusing. And again, this is one of those things, it's not hard. You just have to practice it. The other thing, a drawback I would say, is that they can be a little bit awkward. And so histograms are usually preferable to stem and leaf diagrams. So definitely do some practice on the stem and leaf. I tend to test on stem and leaf because they're easy to include in exams. All right, I just want to go over very quickly a density plot. And what a density plot is a line that smooths the bins of your histogram. So of course, the size of your bins in the histogram can actually influence how you interpret the distribution because it changes the look. We don't have a correct bin size, but we do have some recommendations on, what would look best. Density plots smooth the bins in a histogram, and it reduces the effect of choice, essentially. It makes a shape look less severe. I don't find that we use smoothing the histogram very much in day-to-day life unless we're really talking about long-range modeling. And we are going to talk about later on, you guys will start to notice that in labs that we are adding a smooth line over our histograms. They are not density plots though. And when we get there, I'll explain the difference and what they are. When it comes down to data, you always have to think before you draw or visualize. Every stem and leaf, dot plot, histogram, it tells you a story, but you have to develop sort of a vocabulary to help you explain it. And you have to start thinking about things like shape, center, and spread. And that's kind of a little, hook to get you in for the next video. And we're going to talk about a lot of that stuff. But before you make something like a pie chart or a bar chart, you should check that you have the proper type of data. So for example, they are categorical data. Before making a stem and leaf display, a histogram, or a dot plot, you should make sure you're working with quantitative data. And although a bar chart and a histogram may look similar, they're not the same. You can't display categorical data in a histogram nor quantitative data in a bar chart. So always think before you draw.